And good evening, everybody. I hope everybody is nice and warm on this nice wintry night. My name is Hannah. I'm a volunteer of Pint of Science. And on this side, we have Ty.
Hi, I'm Taichi. I'm also a volunteer at Pint of Science. And tonight we have a special guest who will be talking about, theoretical physics, but more importantly, things that are omnipresent, but very important to us. So we'd like to invite Joost de Graaf for our 9th episode of Pint of Science Netherlands Online.
All
Hi,
right.
Joost.
Hi there. Thank you. Good evening, everyone. I'm Joost de Graaf. I'm a theoretical physicist. I work at Utrecht University, and my specialization is soft matter science, which is essentially all kinds of things which are easily deformable. Very easy descriptive term. And I will be talking about some stuff which are easy to deform and soft and very widely abundant. And I think that will be very interesting for many of you to see how broad theoretical physics can be. And we'll be doing some the more computational aspect of the theoretical physics today. And we'll be showing also some experimental stuff.
So I just wanted to ask, because you said, the other side of how broad theoretical physicists can be, because as I said before, as soon as I think of theoretical physics, I think of someone like Stephen Hawking and the universe, but there's obviously a whole other side of it. So how did you kind of branch off into the area that you're in?
So as a very stubborn 18-year-old, I was one of those people who were like, oh yes, I should become like Stephen Hawking and explore the great mysteries of the universe. And I had a very good time learning about many aspects of physics, including mechanics and statistical physics and various other subjects. And as time progressed, I realized that the grand questions of the universe were not so grand in my mind anymore. And no offense to anyone who does that. They are fine questions and they are weighty questions, but the theoretical physics of materials which have everyday application is actually very exciting as well, and it's more tangible. And I think that was something which I was lacking at the time, and so I was very happy to be able to engage with things which are actually tactile. We'll see some examples of the soft matter materials very soon, and then you'll immediately recognize them as things which most of you will have in your house, at least one of those objects.
Cool. All right, so before we give you the floor to present, we have a tradition of cheersing. So you have your little pint of nine son? Yeah.
Cheers!
So cheers. So Prost.
Prost.
All righty, and the floor is yours.
All right, so let me go to the first slide. It's already shown there. So I was making a rather bold claim, omnipresent and important, and in the next 20 or so minutes, I would like to substantiate that claim, because it is a bold claim, and I wasn't really referring to beer, which is also omnipresent and very important to us, but I'm thinking more along the lines of this bag of silica gel, which is probably omnipresent whenever you purchase footwear, or some other clothes item which you have shipped to you, and I will show you that gels in general are a little bit more present than you would think, and I will also make the connection to beer. So that'll be quite an interesting one, perhaps a somewhat disturbing one. So today's beer menu, if you will, is as follows. I will start off by explaining to you what gels are, and it'll be a very simple description, just some properties. And then we'll move on to the, I've ordered them by how a good beer menu should be. Start off with something light and then progress into the heavier stuff. So then we'll look at the constituents of a gel, specific example of gels to be precise. And then we'll go to the more substantive matters, a darker beer, an open question. What am I actually addressing as a researcher into this topic? And that finishes off the talk, and I will show you some of the more recent results that I have obtained. Okay. So that's the plan for tonight. Then moving on, let us dive right in and go to examples of gels. And here I just have a couple of things. Some of them you'll find in your house. I suspect that many in the audience will have some kind of hairstyling product. I thankfully do not require it. But
I definitely do, so.
But I mean, many of you will have, well, hopefully all of you will have some toothpaste lying around. And an interesting thing about toothpaste is that which you probably don't really immediately think about, there's solid little bits in there, and there's some kind of fluid-like behavior as well. And the solid little bits, you can use them to, well, they remove the plaque from your teeth by the scouring action. So we will talk about the solid little bits in a bit. And then next to that is the little blue balls, and they are the things which are in the silica bag. So the one which was on the front, and those are the things which you're not supposed to eat. And what you may use them for in your daily life is to dry materials. So if you have a very damp room or some product which you want to dry, you can put the silica beads there, and they usually change color once they've absorbed the moisture. The other thing which we're seeing here is a jello type thing. So that's just a food grade material, probably some kind of raspberry flavor if you ask me. And then the final thing which we are seeing here is something which most of you will recognize as this gel electrophoresis for DNA. So what you see here is the DNA profile. I have no idea what DNA profile this is. Don't ask me about that. It's just some Google image that I stole. But all of these things are gels. And so I think I have made some kind of argument that gels are omnipresent. At least in your daily life, you will encounter gels on a regular basis. And you also have gels which are useful for industrial processes, such as the silica beads, or even in medical or criminal investigative type settings. So examples of gels. But what is a gel? Because I mean, clearly there's a lot of different things here. But what would I characterize a gel with? So let us go on. And just a caution, I'm the theoretical physicist, so not an experimental person. These are not my images. References at the bottom. But what people have done here is they take very detailed microscopy. So I think this will be electron microscopy images of the internal structure of the gel. And to the right, to the left, we see this very coarse, open, porous structure, which is of the blue, which is essentially the material of the blue balls. So those are silica beads. And on the right-hand side, we see multiple images of gels, which are more in the genre of the food-grade quality jello thing. So in this specific case, it's gelatin with a little bit of starch mixed into it. That does not sound very appealing, and yet we will eat it anyway when presented with a very nice color. So
Add the flavor.
Yes, that's true. So the commonality between these two images, as you can probably see, is that we have some kind of solid-looking structure and lots of holes. So if I'm talking about gels, then I am thinking of this, or at least that's the mental picture that I have. When I think of gels, I think of some kind of lattice structure And the reason why I took the Eiffel Tower as an image, I will come back to in a bit. But something with holes in it, and those holes don't have to be uniform in size. They can have different small holes and then a few larger holes. But so that's also happening in the Eiffel Tower. You have lots of little lattice works, but then also larger holes in there. And this is really how you should think of a gel. It's a connected network with lots of pores in it.
So would this be one of the defining properties that you would, when you're defining if something's a liquid, a gel, a solid, it would be when it's this combination of these solid features with lots of pores and holes within?
Precisely. And that's what gives it also many of its appealing properties, because if I squeeze out my toothpaste, then it squeezes, so it flows. And obviously that's a desirable property. That's a liquid-like property, which is associated with the water, which is in the holes. But then it also has this thing that if I put the stripe on my toothbrush, it will not run out into the hairs of the toothbrush, which is a much more solid-like property. And so gels, through the fact that they have these network properties, are able to combine both solid and liquid-like properties. And that has to do with the microstructure of the material. So that's essentially my definition of a gel. Then how does one go about making a gel? And here, okay, now first of all, why is this useful? I have already forgotten that we have to start with the lighter fare first and not the slightly heavier stuff. So why is this useful? Well, immediately when I see an open pore structure, I would think of a sieve. And that's one application of a gel. And I will get to why the beer glass is there to begin with, and why we had that on the opening slide in a second. But the first thing I want to draw your attention to is this gel electrophoresis of the DNA. And so what happens is, if people have the DNA strand, it's super, super long. So it's like this cable. And then, they cut it into tiny pieces, not too small. And what happens is they put it on one side of the gel, they put an electric field on it. DNA, I don't want to go into the full details, moves in the electric field upwards. Longer pieces will get snagged on this gel porous structure more readily, so that's the lower stripes, and then the shorter pieces move upwards. And of course, if you cut it up in a certain way, then you will be able to get this nice profile, and you can compare it and then say, clearly this person on the right is related to the person on the left, or person on the right was the murder victim and person on the left was the perpetrator. I don't know what this phoresis was about, but one could imagine such things. So that's kind of that. And then turning to the beer, because I'm sure everyone was dying, well, maybe dying to know is a bad word, but what this beer had to do with gels. And so I didn't know this until I was invited to do the Pint of Science, because I was kind of wondering how one was going to bridge the beer drinking and gels. And I found out that silica gels are actually, well, the ones that you can eat are used to finish beer. So beer in and of itself is... Well, no, it's no longer in your beer, thankfully. But so what they do in the brewing process is they pass it they can pass it through a silica filter. And what happens is that some of the proteins in the beer, which would otherwise make it, I think, flat or kind of, when there's a little bit of material in your beer, they can take it out using a silica finish. So that was actually quite fascinating to learn. So just by doing this, I've learned something new about my topic. And that's one aspect of this. Why is this useful? Well, you can use it to filter stuff. The other thing why it is useful, and that's this little slide, and it comes back to this Eiffel Tower structure I was talking about, is I have water, the most common medium on Earth, or maybe in the case of paint, it might be some kind of oil, but we're mostly turning to water-based paints presently. Now, I want to make a paint, and I have a bunch of pigments. And the pigments are colored, and they're solids. Now, as a consumer, you really want your pigments to be homogeneous throughout your fluid, because you have to take the stir stick and get the gel and you get all the material back, and you want to make it nice and homogeneous. That is sometimes quite hard to do. However, pigments are heavier. And most solids are much heavier than water, so we would expect them to all sink to the bottom. Now, if you make the pigments in such a way that they form a gel structure, you can keep them suspended in the water. And maybe to turn to the toothpaste, you also do not want to have all of the scouring agent of the toothpaste in the very bottom of the tube, and then you squeeze it out and it's like mostly mint-flavored water and a clump of sand. That would be extremely unappealing. So this is one of the things where people would want to make gels in general. And then go on to that. So one of the ways one can make gels, but this is by far not the only way one can make gels. Go to the window. Is using colloids. And what are colloids? Well, colloids are very small particles. So if I think of my toothpaste, then it would be a very fancy toothpaste if it had all these tiny little spheres in it. Usually it's more like chunky. But in the academic world, what one can do is make these very small spheres, and I'll show you how small they are in a second. Scale bar, by the way, is 5 micrometer, but I'll give a small comparison of what that actually means in human readable units in a second. And so you can make spheres, they can make them stick together very, very hard. And so by preparing it in a certain manner, you can get the spheres to stick together, and this is a 2D representation from a lab in Oxford, and you see that they form this kind of network spanning structure with lots of open things. And of course, if you can do it in 2D, you can also do it in 3D, and the toothpaste is a 3D product, so probably not containing some spheres. Now, I've talked about these spheres. How large are they then? So if I have this human hair, it's just very thin human hair. This scale bar is the rightmost scale bar is 4 times larger than the scale bar on the left. So this so one of these colloids can fit in 1/20th of this hair. So 20 of these tiny spheres can fit on the width of a human hair, maybe a little more, but that's the kind of size we're talking about. 1,000th of a millimeter, roughly speaking. So it is quite small. And that has to do with, if you have it that small, then you can make these kind of gel network structures relatively easily. But that goes maybe a little bit.
Does the size of the colloids kind of give the different properties of gels? So would you have larger colloids in more solid gels, or is it more just how built up they are?
It's more about how the network is branched and how fat the arms are, essentially. Though, of course, depending on what type of colloids you use, it can also influence the network. And in the case of, say, the Jello that you eat, it's not solid spheres. It's more like polymer chains. So, just
a reminder to the audience, if you want to ask any questions, please just do type them in the chat, and we'll pop them up and ask.
So yes, I wanted to emphasize that these are very much lab colloids. So spheres are sort of the academic workhorse, and if you go to a, say, more industrial setting, then I think even the suspension on the right, which has many kind of coarse spheres and little potato shapes of all different sizes crushed together, that's more what you should think of in terms of what will be in your toothpaste. the spheres are probably also not very good at actually getting the plaque off your teeth. I would suspect. I'm not an expert on that, so don't pin me down on that. But there's a very big difference between what people would use in industry and then the model systems that one would study in academia, to model what actually is going on in industry. So that brings me to what is going on in industry and what is interesting here. And this is work that I was very fortunate enough, I was very fortunate when I was working in Edinburgh to be involved in. And there is an experimental group there led by Professor Wilson Poon, and he has industrial collaborators, and he was studying gels. And what was he specifically studying? Now I have to switch back to the slides and hopefully play this movie for you. So what he was looking at was he made a gel and then was looking at this interface as it was sedimenting down. Now that is a very, very simple experiment, you would think. Like, is this really what one does at a university? You know, mix a gel and then look at the interface going down? Well, yes, it turns out that is a thing which you can do at a university. So let me play it again. Go ahead. And so really what we're seeing here is this interface going down. And so, yes, at a university, it is not just sufficient to look at it. One should also characterize it somewhat. So what his student did, and not me, was he measured where the interface was with respect to the bottom. And then, you know, time is 0 is the 1, for instance. So this is the height. And so if it's at time 0, stopped like this, then it's at height 1. And then it stays at height 1 for a little while, rapidly starts dropping, and then if I'll play the movie, oh, come on, no, not the next slide, you're spoiling it. Once it's almost at the bottom, it sinks very, very little. And why is this appealing, or like why is this a relevant question? Well, if you're an industry person and you have your bucket of paint, this is the thing which you're interested in, that very first regime where the sample is kind of steady. Because that's when the product is good, right? No one wants the paint to be all at the bottom. This plateau has to be as long as possible. Obviously, time in university is finite, so people tend to make the gel as weak as possible, such that it collapses as fast as possible, because you don't want your grad student to wait forever. But this plateau, stretching it as much as possible, is what people are interested in. And then also, why does it collapse? Like, what is underlying this process of collapse? So that's what is interesting. That's what people were curious about, and that's at kind of with the point where I got into this problem. And so obviously, you know, the situation is annoying when your product has demixed like this overnight, and your customer starts tweeting about their product being all messed up, and then you lose customers and so on. So that can be a bit of a financial burden for you. But if that happens in, say, a medicine, if a medicine were to be made using a colloidal gel, and that has demixed in such a way and you don't immediately see it, well, the dosage could be different from top to bottom of the vial, and that could potentially be dangerous. So that is another reason why this could be very interesting to study. Why does this happen? Now, I don't like to get my hands dirty, and so I work behind a computer and I try to figure out how this works.
Sorry, Joost, sorry to interrupt. I guess my mic was a bit off. Is that one of the reasons why they mix paint before they give it to you?
I was going to say why you always shake it.
Yeah.
Well, yes. So they do. Properly mixing it is not trivial, so you have to be quite aggressive. Like stirring it up with your little stick is usually like a last ditch effort to save it. But yeah, the properly homogenizing a paint is quite an aggressive process, and so they do tend to shake it up. But in principle, we're talking about systems which should last in their suspended state their gel-like state for several years, right? So if you want your toothpaste,
it's why when you have an old tin of paint, you do after a while you see it's kind of quite thick at the bottom and it's more fluidy at the top. Yeah,
and also if you open up a toothpaste from like the couple of years ago, then it will probably be somewhat mixed. But what is most interesting is, of course, the rapidity of this process, like why it's falling down. I will spoil that is not yet fully understood. So anyway, so what have I done? Well, the first thing which I do is like I looked at the formation of these gels, and that's what I wanted to show you, because it gives you a flavor of the kind of research that I do. And so I simulate things. And what does that mean? I just make model colloids, which are these spheres, because academics like spheres, and I put interactions in them, and I make a computer simulation which simulates the dynamics accurately. And as you can see, this is a video this time is being sped up as the video is progressing. You see that these spheres, through their interactions, and I take a small slice through the sample, are forming this gel network. And so there's a slice through this 3D box on the right-hand side. And so what you see is that indeed my simulation works, if only by virtue that it forms this system-spanning network with holes in it. So I'm apparently good enough to make gels. So let's see that again.
So when it's in this state, you would expect it to be more fluid, and as they come together,
fully
solidify to the gel.
Yeah. So now it's become a gel proper.
So this is what's happening when you set your jelly in your bowl. It's slowly all the colloids are coming together.
Yeah, in a certain sense, yes. It's more, I think, what would happen in the tin of paint just after mixing is stopped. Okay. So then, because of what I said before, your pigments are heavy. This simulation I showed you just now was without gravity. So what happens when you switch on gravity? That's the question that I asked. And from left to right, I just increased the density of the colloids. So say more pigments on the right, redder, fewer pigments on the left. And as you can see, you form a gel, but it kind of crumbles because it's essentially an Eiffel Tower on the left, which is poorly constructed. People were very stingy on the building materials, and so consequently it doesn't support its own weight. And on the right, people invested more into the building materials, and it can support its own weight for longer. That's how you should see this. Is that reasonably easy to understand? Should I show it again?
Yes, go for it.
So this is both forming and sedimenting. And obviously, this is the part where not enough ingredients have been added to the situation where we immediately see this rapid sedimentation. Now, this is with gravity.
Related to kind of the layers of the colloids that you would have. So you're saying it's not so much the size of them, but how built up they are.
Precisely. So what on the right hand side, there's more colloids. So the network is more built up. It can support itself more vigorously against gravity. So yeah, if you're thinking about it, is really like an Eiffel Tower with much beefier girders to keep itself propped up.
So Joost, do we have a question from Guilherme? So I'll bring it up for you. So it's about how do these gels compare with those non-Newtonian fluids, like a mix of water and cornstarch?
Okay, so this gel will behave non-Newtonian, but the water and cornstarch one is the one where it's shear thickening. Is the technical term, which just means if you bang it with a hammer, it will resist more, and the more you bang it, the harder it will resist. Whereas this clearly has the property, if you squeeze it, it will flow, because that's what's happened with your toothpaste, right? So it's perfectly fine in its nice shape in the tube, and if you squeeze the tube, it will start to flow. But if you leave it on your toothbrush, it will not immediately start to flow under its own force. And if I bang my toothpaste with a hammer, it will go all over the place. So that's. I hope that answers the question.
Yeah.
So now I have this gel, and I have kind of omitted one very crucial thing, because I'm a physicist. So I try to do this as minimally as possible. And in the gels that you've seen thus far, the ones that I was simulating on computer, I have omitted the fact that there's water. So these are kind of gels in space with fake water. So they move about a little bit, but the water is not taken into account properly. So what happens when we do actually take the water into account? And that's something very interesting. You can see that now the dynamics is much more vigorous. So on the left, if you compare it to the right, to the red ones, you see that the left sample just instantly collapses. Whereas if you are, so I'll show them one after the other. Slow, all the interfaces are at the same height, roughly speaking. And, as soon as the density of the gel becomes strong enough, it starts to support its own weight. So all sedimenting very slowly. And if you add the fluid, then the sample on the left is instantly killed, whereas the sample on the right still has this strength against both gravity and fluid flow now. And so that's the major innovation that have been working on. It's not yet published because I'm a bit slow on that. But how can I understand this? And I think that's the last thing I want to show you before I get into the wrap up. How can I understand this? Well, fluid flow is kind of ripping these arms apart. So the gel is sedimenting, and the fluid in the bottom notices that particles are coming in. It needs to go somewhere because the particles are coming in, and it can't be where the particles are. So fluid flow has to move up, and as it moves up, it pulls apart these forming strands. And so it's not just that you've been stingy on your building materials, but someone is actively destroying your Eiffel Tower as you are constructing it. And so that's an aspect which hadn't been reported on. Now, beyond that, that's the summary. Density provides strength. Flow destroys forming open structures. And so the big unknown is still, why is this happening? Well, I have some ideas as to why it's happening, but that's a story for another time. So the takeaway message, I hope I've convinced you that gels are omnipresent. They are important for many applications, including the making of beer. Why they collapse is not yet fully known. We have some ideas on that. And you can simulate them. And as a theoretical physicist with a computational kind of focus, that is something you can do at the university. And lastly, I would like to thank you for your attention. With that, I have come to the end. Are there any questions?
Thank you very much. We'll give another cheers to gels.
Yeah.
Cheers.
And if you have any questions from the audience, please feel free to put them into the chat. Yes, it was very interesting. So it's really, these colloids are everything when it comes to the gels, and it's very much about the structure of how they're built up. But as you said, they're not just floating in space. It's very interesting to see that with the fluid that they really rapidly change.
Yes, the structure is very much modified by the interaction with the flow that the forming structure generates itself. So that's quite a rich dynamics.
I guess for me, initially you're mentioning or using the use of silica gels when making beer. I was curious, is that for all beers, or is that just more purely for lagers, ales, or is that something that you didn't delve into
I
further?
have no idea. I found this on
Yeah.
a quick Google search, like how can I tie this event
Gels.
of beer making to my topic of gels, and I was very surprised that it was actually used, and a little disconcerted when I was thinking of these bags which didn't have "do not eat" written all over it. But
It's the first thing you think of when you think about them.
but there's food safe versions of that. Otherwise, it would have not been used. I undoubtedly. It will not be in your beer. Otherwise, it would be like sandy chunks in there. You would probably notice that.
So I'm a big fan of ales, so they tend to have already a bit of a sedimentary
Yeah.
if you let it sit
now,
for a while.
now
So-
I'm concerned what that is.
yeah, and I'm thinking if that's also filtering, yeah, what's the remaining part? So yeah, but that is quite enlightening as a beer lover. Good to know.
And then, yes, just to ask you before we finish up, because we are coming up to time. So obviously you've been quite passionately working on gels for a while now, and as you said, that the field that you're in with theoretical physicists is quite broad and interchangeable. Is there anything that you've really got your eyes set on of where you would like to go next with your research?
Yes, there's a couple of things. So one of the things which I'm very curious about, and there's students of mine working on, is how bacteria move in mucus, and specifically, one would think, and it's also very topical, of course, mucus of the lungs, which is a protective layer, and there's many things about. So people always think that's a bold claim. I should be careful with the bold claims. But many people often think that, bacteria and there's biology, so that's a very complicated system, and there's probably all kinds of, body defense mechanisms. But what people have recently started realizing is that many of the defense mechanisms are actually also very mechanical in nature. Mm-hmm. So if you have slime, it is hard to push into as a bacterium. And there's other very curious aspects of that, which have recently been discovered and which have made people very enthusiastic about modeling that kind of scenario.
And so is it easy to, the things that you're working on with the gels and what you're doing here with the colloids, is it easy to apply that to something? I mean, because it sounds like a totally different universe to me, but then obviously if you'd want to go working from one to the other, do you apply it in the same way?
Yeah, so some of the computational techniques that we apply are the computational techniques are kind of very interchangeable between the various things that I'm interested in, but especially when it comes to that project. If you do physics, you'll get a very broad training, so you'll have lots of techniques at your disposal, and so that's also what makes physicists so often very versatile in what they can, the kinds of problems they want to tackle, and maybe also the kinds of problems that they think they can tackle. So that's how I see it, and usually some equation system we could try, or some numerical techniques, and it'll be fun to try. So that's how I see it.
Well, thank you very much for your time, Joost. To all of our listeners, thank you very much, and hopefully you enjoyed our 9th episode today. And don't forget, we can always watch these episodes back on YouTube and Facebook. And if you're ever interested in some of the more of the articles we've written, we do have a blog as well. So don't hesitate to read that as well. Thanks again, and thank you again, Hannah, again for being a wonderful host with me. And thank you, Joost, for an enlightening presentation again.
All right, thank you very much for giving me this opportunity.
Have a good night, all.
Bye, everyone. Night.